The next project is in computer science by Samuel Pritt. He's homeschooled in Walkersville, Maryland.
Thank you. Good afternoon, everyone. I'd just like to thank the Siemens Foundation and College Board for hosting this event, and thank you also to George Washington University, and thank you all for being here. My name is Sam Pritt, and my work's entitled Geolocation of Photographs by Means of Horizon Matching with Digital Elevation Models. Geolocation is the process of determining where a photograph was taken. This is a major problem. Applications include counterterrorism, phototourism, community remote sensing, which is an environmental application, and robot navigation, and also disaster relief even. And it's relatively unaddressed. Despite the availability of GPS devices, a recent study showed that only 4% of photos and videos on the internet have location metadata. Counterterrorism is a big problem because terrorists take a lot of photographs to document training and operations. They even post them on the internet. Intelligence analysts need to know where these photos were taken so they can use them as a source of intelligence. Currently, the only way to do that is manual geolocation, which is extremely time-consuming and often unsuccessful. So there needs to be a reliable, automated way to do that. So this problem has been approached in a variety of ways, but generally the strategy has been to match a photograph against a large database of already geolocated photographs. The problem with that approach is that there has to be a database, and that's only going to happen in large populous urban environments. Horizon matching is a different approach that doesn't have that limitation. There have been two other horizon matching methods previously published, but they're both very limited. For example, neither one of them can geolocate ordinary photographs, and they're both limited to very small search regions. My algorithm is a horizon matching algorithm and it uses digital elevation models, which are trained elevation data sets. I got these from the U.S. Geological Survey. They're free for download. And the key idea is to generate virtual horizons from these digital elevation models and then match them against the horizon from the photograph to geolocate the photo. So the algorithm basically follows a four-step process. First, the horizon curves are generated from the DEM. Next, the photograph is inputted, and then the algorithm extracts the horizon curve. Then it matches that curve against all the curves from the DEM, looks for the best match, and outputs the location. So to generate the DEM horizons, the algorithm projects all the trained points to every point on the ground sampled every 500 meters. And it projects them to a panoramic 360-degree image plane. So at each point on the ground, we have a panoramic view of what the horizon looks like. Now, there's two reasons for projecting to a panoramic plane. First of all, when the picture was taken, we didn't know which direction the camera was facing. Second of all, this allows it to be a pre-processing step that only has to be executed once for any DEM. The next step is to extract the horizon curve. Currently, I perform the extraction curve manually. It can also be done automatically. That has been investigated before. However, this curve is flat, and in order to match it against the curves from the DEM, which are in that panoramic geometry, we have to transform it so that it will be curved. So we apply a mathematical transformation shown here, and that will warp it into that curved shape. The next step is matching. We match the photo curve against all the curves from the DEM. And the match is performed simply by aligning the two curves on top of each other and calculating the area between them by integration. A smaller area corresponds to a better match. Here's an example of a match. You can see here the yellow is the curve from the photograph, and then the red curve is the curve from the DEM. Finally, we have to search over the entire search region. The search space is highly complex. It's a 5-dimensional search space because we have the easting and northern coordinates of the camera on the ground, and then we have the 3 angles of rotation of the camera, roll, pitch, and yaw. And here, this image above shows the search space graphed as a function of camera position. So the vertical axis is the area of a match. So high values are good matches, or bad matches, and low values are good matches. And then the x and y coordinates are the easting and northern coordinates of the camera on the ground. And you can see that this search space is extremely complex. There's no overall pattern. So the only way to search that is an exhaustive global search. However, once you find the best match from that global search, then if you graph the search space in a localized region around that good point, as shown in this image here, now you have a very nice contour. So it's possible to perform a downhole multi-resolution search on that to pinpoint the location. The same thing happens for the angle. And here in this image below, it's the same function, except instead of graphing the area of a match, we're graphing the area of a match against the angle of rotation of the camera. So we do a global search every 1 degree, and then we pinpoint it by a multi-resolution search. The algorithm was implemented in Java on a Windows PC, and it's very fast, even on a PC. It can search 7,600 square kilometers of terrain per minute. So it could search the entire state of Maryland in only 4 minutes. Some things I did to reduce the runtime are CPU multi-threading. I ran it on my PC. I have 4 threads, so I CPU multi-threaded it. I also reduced the horizon curve resolution. The photos I use are big. They're about 3, so I'm working with horizons that are roughly 3,000 pixels, but I found that I could compress that to 200 pixels, greatly speeding it up without compromising the accuracy. And finally, I increased the DEM step size to 500 meters. I tried different values, and I chose that as a trade-off between runtime and accuracy. I took a wide variety of photographs to test the algorithm. So I had desert scenes, vegetated scenes, even partial horizons, beach scenes, and even indoor scenes with horizon visible through windows. I took photographs in 6 different states on the east and west coast, and I had very large search regions of 300,000 and 500,000 kilometers squared. Now, if you compare that to the only 2 other horizon matching methods published, they're both limited to less than 900 kilometers. I tested 100 photographs. Of those, 83% geolocated correctly with a mean error of only 300 meters off. And here I've graphed the errors where here the y-axis is the camera view axis and the x-axis is the error orthogonal to the camera view axis. So these errors are transformed into the geometry of the camera, and you can see they're spaced pretty much symmetrically around the camera, the origin, which is what we would expect. And here are my search regions. Here, the search regions are outlined in red boxes, and the yellow tacks on the map are locations of photographs that I geolocated successfully. So I have the East Coast and the West Coast. Now I just want to show a few examples of photographs I geolocated and how I geolocated them and the results I got. This first one was taken in Carpinteria, California. And you input the photograph, you can see the horizon very nicely. And then the algorithm takes that horizon and matches it and then finds the location. And here, this is standard output that the algorithm, it outputs these, showing the curves. So after it performs a match, the yellow curve is the photograph horizon curve, and then the red curve is the curve from the DEM at the location that it found to be the correct location. And you can see that they match up very well. The peaks and the dips line very closely. And so that was a correct match. It geolocated successfully. This one was from the Mojave Desert in California. This is another good example of how the peaks and the dips really line up when you have a good match. Again, Prescott, Arizona. This one's from Prescott, Arizona. This photo was taken in Winchester, Virginia, so this was on the East Coast. This one was my personal favorite. I took this picture in a Jack in the Box restaurant in Hesperia, California. When I took it, I wasn't planning to use it for testing. I was just taking a picture of myself. But when I got home, I noticed that through the window, you can see little bits and pieces of horizon through between the buildings. It really isn't much. If you look at the curves, the yellow is what was in the photograph. There's not much at all. But this still geolocated successfully. And so this is proof that the algorithm doesn't need a full horizon to geolocate a photograph. It only needs a small amount of horizon, and it can even be bits and pieces. And finally, this one was taken in Sloan, Nevada. This is just another of my favorites because it was taken out the back of a car window. But once again, it's a very nice match. You can see the peaks and dips line up very nicely. Now, I'd like to go through a few examples of cases where my algorithm fails and what I did to address those problems. These are curvature of the Earth, DEM inaccuracies, and atmospheric refraction. Curvature of the Earth happens because USGS DEM elevations are measured relative to an ellipsoidal approximation of the Earth's surface, known as WGS 84. However, my algorithm assumes that the Earth is flat. So when you're looking at mountains relatively close to the camera, that's not much of a problem. But when you look at peaks very far away, such as in this photograph of Lake Mead, then there's an offset there. And this photograph failed originally because there's a very distant mountain peak. And you can see when the curves were matched up the first time, there's this peak over here where the red is too high because the algorithm overestimated the height of that peak because it wasn't accounting for the curvature of the Earth. So I had to add a mathematical correction to fix for this error. And then I ran it again, and this photograph geolocated successfully. And now when you look at the curves, there isn't that discrepancy anymore. Another problem is DEM inaccuracies. This one was harder for me to discover because I wasn't expecting it. But the DEMs I use from the U.S. Geological Survey are very old. And they're not very up to date. And since they were created, things have changed. Elevations have changed. In this case, it was highway construction. This highway wasn't there when the DEM was created. So when I took the picture, I was standing a good 25 meters lower than the DEM thought I should have been because the elevation has been changed. So interestingly, the error here is not in the horizon itself, it's in the position of the camera. Now, if I was looking at mountains that were very far away, that wouldn't make much of a difference. But these mountains here are less than a kilometer distance. And at that close distance, minor errors in the camera height can drastically change how the horizon looks. And that caused this algorithm to fail. So to address that, in the future, I'm going to incorporate camera height into the search space. That will make it a 6-dimensional instead of a 5-dimensional search space because we'll be searching over the camera height as well as the eastern and northern coordinates of the camera on the ground. But that will allow us to correct for these DEM elevations errors. And finally, atmospheric refraction is another problem. This is a more rare problem, and it's related to curvature of the Earth. It happens because the Earth is curved, but the fact is that light bends as it travels through the atmosphere. And so these islands, these are more than 80 kilometers distant. They're very far away over the water. And because the light bends, the algorithm it's assumed that those islands were higher than they actually were. And so that caused that photograph to fail. But this too can be fixed by a simple mathematical correction. In conclusion, I've introduced a new method for geolocation of photographs that works by horizon matching. It matches a photograph's horizon curve against horizon curves generated from a DEM. It's fast, accurate, and reliable. 83% of my photographs geolocated successfully with a mean error of only 300 meters. And it searches 7,600 square kilometers of terrain per minute. It doesn't have limitations that other methods have. It can geolocate ordinary photographs, and it is not limited to very small search regions. Also, it doesn't rely on a database of already geolocated photographs. And finally, it has important applications, including counterterrorism, phototourism, and remote sensing. And I'd like to give two other examples of applications from my personal experience. I was recently contacted by a Lockheed Martin engineer who was working with FEMA. They had a bunch of pictures of damage from Hurricane Sandy. Somehow the GPS data for these photos had been lost, so they did not know where the pictures were taken, and they needed to find out. So he actually asked to use my software to geolocate them. A few weeks ago, also, I was contacted by a group of entrepreneurs in the DC area who are starting a phototourism business. The idea is that they want to create an online web application so that if I want to visit someplace in, let's say, Taiwan, I can search for it in their application, and it will pull photos off the web from that area to give you an idea of where I want to visit. Obviously, that's going to require geolocation, so they want me to help, and I've actually started working with them already. And so, yeah, I expect to see lots more examples of this. This is a big problem, and it's a current problem that keeps coming up. So I patented this idea. I'd actually like to thank my patent attorney, Jack Barufka, for helping me with that. And that's all I have. So thank you for listening.